y is negative cosine of y. We have to deal with the limits, though. Sorry, I didn't leave myself enough room there. Let's see, can I just move this over? Sure. So let's plug in those limits, and you get the integral from 0 to pi over 2 of plugging y equals x into that. I get negative x times cosine of x. That's going to be a problem, isn't it? Minus negative x, because the cosine of 0 is 1. Let me clean this up just a bit, and then we'll deal with it. So I'm sure all of you could have gotten to this stage, and now things get a little bit harder. I'm sure you know the antiderivative of x is x squared over 2. So that one's going to be easy, x squared over 2. So to do this one, you have two choices at this point. You can either do integration by parts, or you can just flounder around and take a guess. You know, I kind of favor the floundering. So let's take a guess. Let's see, I think it's going to be x times the sine of x. Now, that's not what it is, but this will get us there, trust me. So here's the deal. If you just take a guess, then you have to check your guess. Here, let's go do the checking on a separate sheet. So let me go down here to the bottom and pick, there it is. Okay, so what we're trying to figure out this. And so my guess is, I don't know, maybe it's x times sine of x. Well, let's give it a try. If this were true, then the derivative of x times sine of x would equal x times cosine of x. Well, let's check it out. Using the product rule, the derivative of x times sine of x is x times cosine of x. It's feeling good. Oh, but I have to add on this. So I have this product rule business that I have to deal with. Okay, well, let's see. Can I sort of fix that? I'll bet I can. What if I do this? If I just add in or subtract off, add cosine of x to this? Try this. All right, is that one correct now? I think you can probably guess that it is, but let's just double check. So to double check, you would just do the derivative of this. The derivative of that is, I just erased it, didn't I? X times cosine of x plus sine of x. That came from this using the product rule. And then this minus sine of x. And like magic, those cancel, and you're left with what we wanted. So that's one option. It's an option. You don't have to use integration by parts if you don't want to. However, some of you might want to. And so if you want to use integration by parts, here's how you do it. U is equal to x, du is equal to dx, dv is equal to cosine of x dx, and v is equal to negative sine of x. Or no, not negative, just sine of x. And then you do the integral of u dv is equal to u times v minus the integral of v du. So as long as you sort that out, you'll get the same thing as this up here in the end. So there's the antiderivative though. So let me go put that back up at the top. Hold on a sec. Copy this. Go back up. Here, just a sec. It's going to take too long. There we are. And so that goes right here. Paste. Okay, let me get rid of the one that is wrong. So that one's wrong. Put this one up into place. And be careful with parentheses. There we go. So anyway, this is the final step. Now we're going to plug in x equals 0 and x equals pi over 2. What is that? That's going to be, okay, it's going to be all right. This is going to be pi squared over 8 minus, this is my pi over 2. The sine of pi over 2 is 1, so this will be minus pi over 2. The cosine of pi over 2 is 0. And then I plug in what I get when I plug 0 into all of this. I'll have 0 minus 1. So that will be, what is this, 1 plus pi squared over 8 minus pi over 2. Yeah, that looks good, doesn't it? There's no back of the book to check. So that's going to be the correct answer now. So how's that? Does that work for you? It was probably just that one part, right? That was the hard part. So so anything else that we had that brought either suffering or just you want to just share your joy? Maybe there's some joy here. Arctangent? Was arctangent? I don't think arctangent was there. I'm always on the lookout for an arctangent, so be aware. Okay, so what about this stuff down here? You understand what that symbolism means? Because this is what I used on my quiz, is I used that symbolism. Maybe we should take a look at one of these. Which one did you have to do? Oh, 9. Oh, it's the one I just circled. Good. Yeah, this is a good one. Oh, I like this one. Yeah, let's take a look at number 9. And then we'll do the quiz. It's all right. I need to delay anyway. Going too quick. Okay, copy and delete. Go to the end. Here we are. Okay, so there it is. Isn't that beautiful? So we're going to, first things first, I should have done this on your quiz, but I did not. I don't have grids on your quiz. So normally I would put a grid on the, for you to draw on, but I didn't. So let me just draw. Yeah, I guess it's kind of not really necessary for this one. So y goes from 0 to 3. So 3 up here, here's 0. And x goes from 0 to y. So I guess we're talking about this region right here, because that's x equals y. So there's a temptation, whenever you set up a double integral, you're going to feel the pull, the temptation to do it like this, dy dx. However, in this case, it's going to be way better if we switch it around and do dx dy. You see, if we did dy dx, let me set up the limits just so you see what they look like. But this will be too difficult. So dy dx means that you have delta x is on the small side of my little representative rectangle. So it goes on the outside. We're going to practice this some more today. So if you're still a little fuzzy on this whole little rectangle thing, we're going to work on this. Okay, so we've got that there. The limits, let's see. So the knife begins over here at x equals 0 and ends over here at x equals 3. So that's this part. And then if you think of the sort of the bottom of the rectangle is on that line, the top is on that line. So that's y equals x. This is y equals 3. So anyway, that's the way I would set that up if I were going to do it this way. But I'm not, because that's going to be way harder than what we're going to do. And the reason why this is harder is because there isn't an antiderivative that I can write down for this. You can go to Desmos or to Wolfram Alpha. You pick your online computational algebra tool. It doesn't have an antiderivative for that. I mean, it'll give you something, but that something is not, it's not a true elementary function. So anyway, because of that, I'm going to do this the other way. So let me get rid of this one, get rid of this, and that. One more thing to get rid of, this stuff. Okay. Guess I'm getting rid of more than I said. Okay, there it is. Okay, so now I'm going to set this up with my rectangle pointing this way, which is uncomfortable, but the small side is delta y, which means that instead of doing dy dx, I'm going to change this to dx dy. dy is on the outside because the small side is dy, delta y. Now, as far as the limits go, the limits, erase, get rid of all of this, good. Okay, so my new limits, the outer limits, since this is a y, It's where does y? Y goes from 0 to 3. There are always going to be constants on the outside. Y equals 3. You'll never have variables on the outer integral. It will always be constants. So it's like, where do we start? Where do we end? What's the smallest and biggest? On the inside, I'll have functions where x is a function of y, and this will be the bottom of this rectangle, and the top, if you imagine tilting your head on its side so that the left to the right, sort of bottom to top. So the bottom, x equals 0, top, x equals y. Now I can do this. Let's just pound through this. This one's easy now. But yeah, this is the hard part, setting it up. On the quiz, I have, why did I pick so many? Well, it'll be okay. Anyway, you just set it up and then do your best to evaluate. And if you get the answers, there will be hopefully some joy in the answers. I tried to make it interesting. Not hard, just fun. Okay, so let's see. This is going to be e to the negative y squared times x, evaluated from x equals 0 to x equals y. That's the inner integral. So that's going to be e to the negative y squared times y minus 0. So I'm going to leave out, well, here, I'll put the 0 in. So there's the inner integral. Now the outer integral, y e to the negative y squared. Here I'm going to use substitution. Y squared du is negative 2y dy, so that this becomes the integral of e to the negative y squared times negative 2y dy, and I have to put a negative 1/2 out front to balance out the negative 2. Now I can do my substitution. I know I'm doing this super quick. Negative 1/2 integral of e to the u du, which is negative 1/2 e to the u, which is, in our case, negative 1/2 e to the negative y squared. Y goes from 0 to 3. So that'll be e to the negative 9 minus e to the 0, which I suppose we could write like this, 1/2 minus e to the minus 1 over 2 e to the 9th. I don't know. You can write it however you want, but this is fine here. This is fine. The quiz, though, it should come out nicely. All polynomials, no substitution. None of that weird integration by parts. You should be fine. Okay, everyone's happy? Good. Let's go ahead and give this one a go. And I will double check, but this morning when I tried this quiz, it all worked out nicely. No decimals. But yeah, no, that's dangerous because when you get a decimal, then all of a sudden you're stuck. So it works by mistake. So do your best. If you make a mistake, I'll try my best to find it. Let me know if I didn't give you enough. This row is good. This one, you need one? There's one more. Excellent. All right, enjoy. My stack, good. We'll get the quiz up here. There we go. mistyped. It's okay. You've already done C. It's like it's not coming out the way I wanted it to. It's all right. C, I have the wrong limit. I didn't type it correctly. It's fine. You just keep going. That's too bad. It's not as entertaining. I'll show you what I'd intended. Yeah, it's like I got the answer. And I'm like, that's not what I remember. And just checked my notes. Oh well. It's probably for the better. It would have been more work the way that I had. Yeah, it's fine. Yeah, it's still okay. It's just not as good as I'd wanted it to be. So. Okay. So some of you are done. Yeah, make sure I get your homework too. Got that in the stack there. Is this homework for you? See. Excellent. We'll get. Draw the region. All right. Hopefully you're wrapping things up here, and don't do too much of these things. Oh yeah, that would be one option. It's not what I originally conceived of, but you're on the right track. Yeah. That would have been a better option than what I was thinking. Same goal. Okay. Anything else you got it set up for me? Yeah, that one's gonna take a little bit long. So, but you got it set up. You have limits on? Yeah, you got your limits. Good. All right, good. All right. Do I have all of them? No. Ah. Now I've got them all. Okay, so let's go ahead and see how we did. Stable. I'll stick this over here. Okay, so the first one, and I didn't actually say that you had to do this. So I don't think anyone, or maybe a couple of you did the region. But what we're going to be doing for Monday is we definitely want to sketch the region. So on the next exam, whenever I have a problem like this, I'll have a grid. I'll say sketch the region. Show me a representative rectangle. So for example, this one. This was nice and easy, a rectangular region with x going from 0 to 1, y goes from -1 to 1. So this is the situation we're looking at. I know it's kind of a poor rendition, but x goes from 0 to 1, y goes from -1 to 1. We have this tall, skinny rectangle. The delta x is on the skinny side, and so that's why I have this with a dx on the outside. So drawing that region is helpful for figuring out what the limits are. In here you put the function. Okay, that's good. So that wasn't bad, and you all got 1, I hope. So when you get done with this, do the integral. First of all, the inner integral, you get 2x, and then the integral. Yeah, it's a bit of a mess, but I got 1. Okay, so I got the next one. This region was a little bit different. So here's what the region looks like. Yeah, it's kind of sketchy there, but so this is my x-axis. I should have labeled them. Here's the y-axis. So you had y equals x, y equals -x. And then you had 0 to 1. So it's this triangle here. And I've got that really weak-looking rectangle. But so my representative rectangle helps me to figure out where my limits are. So the reason for that is that you have to imagine moving this rectangle left and right. And so the rectangle begins here at x equals 0, ends at x equals 1. And so that will tell me my outer limits, 0 to 1. And then each of these rectangles, they begin at the line y equals -x, and then they stop at the line y equals x. And so that's my inner limits. So that's where you're getting your limits. You probably could have just gotten this directly from this, but sometimes you're not given it quite as explicitly as this. So it's good to draw the region and then do your best. So then there's the setup. So the rest of it, polynomial. Hopefully you can do polynomial antiderivatives. Here's my work, though, if you're curious. I did the inner integral, got 3xy, and then evaluated this at y equals -x and y equals +x, and got 6x squared, because 3x squared minus -3x squared gives me 6x squared. Then I did the antiderivative of that, evaluated from 0 to 1, and the antiderivative of this is 2x cubed. So I'm going to do 2x cubed evaluated from 0 to 1, which just gives me 2. So as you might guess, my goal was I wanted it to go 1, 2, 3. It did not do that. The third one, I messed up my limits. Here's, by the way, here's the picture, the way that I have it here. So you have x going from 0 to 1, y goes from 0 up to x squared. What I had intended, but what I had intended would have been much worse. I had intended this. Whoops. Let me cross this out with purple. Yeah. I had intended this to be the case. Y is less than or equal to 1 minus x squared. And the picture would have been this. Let's see, draw this like this. So it would have been like a upside down parabola. And so you would have something like this. And if this were the limits, then the answer would have been 3. So it would have been 1, 2, 3. But sadly, I didn't have that. Actually, it was probably good because this, plugging that into y squared would have been ugly. But the way that it worked out wasn't too bad. So the way that it's written here, yeah, ignore my little cross out there. The way that it's written, here's what we've got. We've got the limits, we're whatever, okay. And then you do the antiderivative. This is the stage at which I was happy that I had gotten the wrong limits because plugging 1 minus x squared into this would have been a little bit longer to deal with. The rest of this is easy though. Plug in your stuff. Here's what I got. And then I got down here, did my antiderivative with respect to x, and I realized something was wrong because I was going to get a fraction. Plug 1 into this, 3 halves minus 1 plus 1, which is 3 halves. Plug 0 in, 0, 0, 0, so that you end up with just 3 halves. So I had noticed, and Luke noticed as well, that if I had made this 30, then all would be well, wouldn't it? So we could have retroactively put a 30 there, and then this would make it the way that I would want. This would be, I guess, 6 halves, and this would be 3. Then I would have gotten my 3 and would have been happy. But I did the best I could. So anyway, 1, 2, 3. It was a typo. I mean, you can see here that that should be 1 minus x squared, but it's good that it wasn't. Okay, let's see. Do I tell you now about this? Oh, yeah, why not? So one of the things that is a double-edged sword, so don't get too excited about the next exam, is when I first started teaching here back in 1997. I had a student who had a Texas Instruments 92 calculator. For those who aren't familiar with the Texas Instruments 92, I have one in my office. I should have brought it with me. It's big. It's like this big. It's literally twice the size of a Texas Instruments 83 like this. So if you imagine stacking 2 of these on top of one another, that's the Texas Instruments 92. It has a QWERTY keyboard. I had to make a decision at that point. What do I do about this kid? Because all the other students were suffering with these. Like, he had the ability to do symbolic algebra, for example, or not symbolic algebra. I think his just did, it did numerical double integrals though. And so he had a leg up on everyone. So back then, I realized, well, I got to do something. So instead of prohibiting him from using his calculator, which I could have done, but I said, just get one that doesn't have a QWERTY keyboard. I ended up, when we get to the next exam, the exam looks something like this. So the quizzes don't look this way, but you can look forward to this. But I got to tell you, this is a double-edged sword. I have the question, and then I have in parentheses, here's the answer. You know, because the kid with the Texas Instrument answer, and so I quadruple check these. So I'll do like that, and down here, of course, if this was the correct version, I would have answer equals 3. Now, what this means is that when you get to the exam, at least for those problems where I give you the answer is worth nothing. So you get 0 points for the answer. So you have to show me where that answer came from. So everyone is on the same footing. So I know that there are a couple of people in here who have Texas Instruments Inspire calculators that'll do the double integrals for you. Maybe you don't know that. Now you do. So we'll just continue the tradition. More on that when we get to the next exam. But I need to tell you that this is not as great as you might think it is. See, the problem is that I'll have someone with question 1, they'll have their answer, they'll do their work, and they get to the end and they have 1/2. And instead of just boxing it and going on, they spend an hour trying to figure out how number 1 is wrong, and they might miss, it might be that there's like they've got a 2 out of place or whatever, but you know, let it go, move on, and then at the end, if you have time, go back. So it creates more anxiety, I think, than it's worth. But I mean, all of my that's the way I've been doing this for 28 years, 27 years. This is my 28th time doing this, so that's the way it's going to be. Just wanted to warn you. I won't do this for quizzes though. So for quizzes, you still have to show your work, either way. Like you'd have, this is what I grade. This is what I'm looking at. I don't care about this. So, in fact, I had a kid try to scam me once, put fake work down and then just put the answer at the end in a box. And I was able to say, no, that's not correct. So, I'm looking at this. It takes me more time to grade, but there it is. So, same thing here. Basically, the way I grade these is this. I'm looking for certain stepping stones. So I know that you're going to have to get here at some point. You're going to have this at some point, and then you've got the answer. So you'll see when I grade the next exam, there will be lots of check marks because I'm looking for these specific stepping stones. And whatever you do, you're going to have to hit those at some point. Like you'll have to have that somewhere in your work. So anyway, we'll talk about that more in a couple of weeks when we have our next test. For now, though, we need to do a little bit more work with double integrals and volumes. I know you're sick of this. Well, we're going to move on. On Monday, we'll be moving on to another, actually, Monday, we take all of this easy stuff and we make it super hard. So I guess I should say it's not, we're changing. Yeah, it'll be okay, though. It'll be okay. But I need to remind you these three things that, whoops, there they are. The three things that we're going to do. And from now on quizzes, also on the tests, not only will I have the problem, but I'll have a little grid where you can sketch the region. So each of these will, I won't have three of them on Monday. I'll probably just have one or two. And you'll have a grid, you'll sketch the region and go from there. So let's practice this with a particular problem that's a little bit harder than the ones that we've had. Sorry, that shouldn't appear. It shouldn't have appeared like that. Just a sec. I can get rid of this. If you give me a minute. I have this the power. Let's see if I do this and change my animations. There we go. Did it disappear yet? It hasn't disappeared. It disappeared. Go away. Okay, it went away. Okay, I knew it would. Okay, it's gone away. Okay, so we want to find the volume between the solid 4 minus x squared minus y squared and the xy plane. This reminds me, I need to get to Kroger today and see if they have any leftover Halloween candy. Because this reminds me of, I almost went this morning and, but I just didn't have myself together. The reason why I say that is because this function is the gumdrop function. So it's about the best I can do here. So if you can imagine, this is what this looks like, sort of like that. It's a paraboloid. It points downward. This is the point 4 here. So that's what this thing is. Even if you didn't know that, I think we could figure this one out just from understanding what basic geometry looks like. So here, let's see, dot, 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 put some dots here. There, now it looks almost like you're looking through, well, didn't quite line up, did it? It's okay. Okay, so we want to solve this thing. I need more room, so I'm going to go over here. So we've got this object. What I want to do is I want to understand what the region looks like. And so since I'm intersecting this, whoops, I shouldn't draw that quite yet. Since I'm intersecting this with the xy plane, I could just set this equal to 0 because the xy plane is at the height of 0 feet above sea level. So basically, I want to know, what does this look like in the xy plane when I slice this gumdrop off to make this delicious piece of candy? Set this equal to 0 and then do some basic algebra, and you find x squared plus y squared equals 4 is what you're looking at. So this is a top-down view of this gumdrop, of this object. If you take Dot's candy, the most delicious candy you could get at Halloween time, you would look down on those candies from above, and you will see this beautiful circle of gelatinous joy. So that's what I imagine when I see this sort of a curve. So let's take a look at this. If we were to slice this thing up, I'm going to make a little rectangle to represent the slice. There's my rectangle. and this side of the rectangle is delta x. Okay, so that's the first part for setting up this double integral. The next part for setting up this double integral is to actually work out the limits. So we have this outer integral. Since the outer integral is delta x, we have a dx out there, dy on the inside. And so you can imagine slicing this gumdrop up into little slices. I don't know why you would just pop it in your mouth and have joy. But as we go across, the slices begin at x equals -2. Slice, 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 chop, 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 and we get over here to +2. I suppose if you had some monster giant-sized gummy thing, you might slice it with a knife. So x here ranges from -2 to +2. Okay, next thing that we're going to do is we want to find the lower and upper limits. So here's where this rectangle stops up at the top here. The bottom is right here. There we go. Oh, that teal or whatever color that is doesn't show up very nicely against the green. But anyway, the bottom to the top. So I need to be able to express those. And I'm going to use this to express them. Specifically, y squared is 4 minus x squared, which means y is plus or minus the square root of 4 minus x squared. So the negative radical is on the bottom, and the positive radical is on top. So when you're given a generic problem like this, where it doesn't tell you what the limits are, this is the strategy. Sketch, draw, do your limits as best you can, and then I guess we need to know what the integrand is. Okay, well, what goes in here is the function itself. The function, so what is the function? Oh, the function is the top, if you can imagine. I want to know how tall this delicious piece of candy is. So I'll need to use the function. The function was this, I believe. F of xy is 4 minus x squared minus y squared. So that's what goes in here. Okay, let's see if this works out. Sadly, this is going to be a little bit more work than we're going to want to do. But we'll get started on it. So I need to do a couple of other things. But don't worry, we will find out what the volume of this piece of candy is. And we can do it. It'll be easier, though, next Tuesday, maybe Monday. I think maybe Monday. Maybe on Monday, we're going to learn a technique for taking this that looks like a nightmare and turning it into something super easy. As you can imagine, there's a price you'll pay, but that price hopefully won't be too steep. Okay, but let's get started at least. So the first step, I won't do the whole thing because the outer integral is a little tedious. It's something I have the answer in my PowerPoint. Maybe I'll just show you the PowerPoint. Maybe that would be easier. Yeah, let's go back to PowerPoint. Yeah, so there's the integral there. So it's the same thing that we had. So here's my integral. Let's see, it's familiar. Now let's see if this will behave over here. Oh no, I don't have the answer in my, it was a different problem. Darn. Okay, well anyway, yeah, I'll get it started, not to worry. Yeah. But we won't do the whole thing. There's a trick we can use next week that will simplify this greatly. Okay, so the first step is to do the inner integral. So 4y minus x squared y minus y cubed over 3. As you can imagine, the problem is when we plug in these limits. Y equals square root of 4 minus x squared. Sorry about my 4. So let's go ahead and plug those in. X equals -2 to x equals 2. And if you don't mind, well, you probably do, but I'm gonna do it anyway. I'm gonna exploit some symmetry here because this and this, these are symmetric about um, the x-axis. So this is y equals negative of that. Then what you're gonna get is when you plug in the upper limit, you'll get the exact same thing as when you plug in the lower limit, only the negative of it. And so you'll end up getting double what you get. I mean, you can do it and you'll find out that this is true. Oh, this is only true with odd functions. This is an odd function, odd powers. So I know that maybe more than your mind has just been blown, but here's what this looks like. So I'm doubling. Basically, I'm plugging in the upper limit and then doubling it. It's a little trick that I use sometimes to do quick mental arithmetic. 4 minus x squared minus 2/3 times the square root of 4 minus x squared cubed. Okay, so I think you can see what the problem is here. This is doable, and I've done it before. I remember doing this each year. It's just that there's another thing that we need to talk about before we leave. And so you could do this. There's a little bit of a problem here and here, but you can expand this, and yeah, it's definitely doable. You'd use integration by parts on that middle term. Oh, that's a problem here as well. Oh, no. This is integration by parts as well? That one might be a natural log of some sort. But anyway, yeah, it's doable. Oh, some of you have in your textbook, in the in pages, you'll have like tables of integrals. You could look these up. Okay, but I'm not going to, because this is hard. So I'm discouraged. I will do this on Monday, though. It will take me 2 or 3 lines. Seriously, there's a trick to doing problems like this quickly. Show you on Monday, though. Okay, so let's go back to PowerPoint land and pull up the next thing that we need to do. The next thing we need to do is learn about how to change the order of integration. And the reason why we would want to do this is if we were presented with an integral and the way that it is set up is too hard to actually do for one reason or another. And so maybe swapping the order of integration might help things. And that's what we're going to do here. So let's do this. And I think I've got a couple of problems like this on your homework where I ask you to, so there's only 4 problems on your homework. 2 of them, it's pretty straightforward. Do the double integral, find the region, you'll be fine. Do sketch the region though. So humor me on this one, sketch the region. I will have it on the quiz on Monday. You'll be sketching the region for me. But for these, what you're going to do is to change the order of integration, let's first of all sketch the region. So see if you can sketch this region. Now, the way you're going to do this is you have to bear in mind that y is between arctan of x and pi over 4. And then x is between 0 and 1. So you want to sketch that region. So what I'll do is on a graph, I will sketch these 2 functions. So y equals arctan of x, which I know we all know what it looks like. It looks like this. So that's y equals arctan of x. And then y equals pi over 4 looks like this. That's a horizontal line. So you have arctangent of x, the blue line, pi over 4 is the red line. And then we have these limits for the x values. X goes from 0 to 1. And you might say, well, wait, how do you know that that intersection happens at that point? Well, it's because I love the arctangent, so I know about it. But the arctangent of 1 is pi over 4. So there you go. So what region am I interested in? I am interested in this region right here. And the way that this is set up currently, Notice that the outer integral is the x, and so currently this is set up this way with a little rectangle like that with delta x. But we're supposed to switch the order of integration, and so to do that, let's get rid of that little rectangle and redraw the rectangle to be a horizontal rectangle. Ooh, that's not showing up well, is it? Let's try a different color. That's a little better. So there's my little horizontal rectangle. Now delta y is the skinny side. So let's see if I can sort this out. So y starts at 0 and ends at pi over 4. Hopefully that part will be the easy part. The y on the outside. All right, shred it up. Yeah, we all got to go to chapel today because not only do we have shredding, but we also have Tavares Taylor. Yeah, that's I know. You don't need to use one of your chapel skips today. Today will be a good day. Okay, but anyway, so then what's x? X starts at this green line here. So x starts at 0 and ends on this curve. So I need to be able to write this curve in terms of x being a function of y. We can do that. X is equal to the tangent. That's the opposite of arctangent. So tangent. So that's the way that's going to shake out. Let's take a look at one more of these, and then I'll show you actually on the homework how this looks so that you don't get scared. So anyway, that would be, I'd be done with this. In fact, let's go look at the homework right now, and then we'll do the other one. Where is it? 15.2? Let's see, it's numbers 51, 52, something like that. Oh, yeah. Okay, so this one, actually, these have you reverse the order of integration and evaluate the integral. So as you can imagine, if you try to do the integral in the order that it's given, you'll fail. And so that's why they want you to reverse the order of integration. In fact, instead of doing the ones that I have, let's pick one of these that's not terrible. Ooh, that one looks terrible. We're going to do it anyway. So give me a sec. Grab this. I'll put it here. Okay, done. Copy and delete. Yeah, let's do that one just to illustrate this idea of changing the order of integration and doing the actual integral. So there's our start. So first things first, you should sketch this. So right now, the way that this is written, notice that y goes from 0 to 8. So we have y equals 0 to y equals 8. X, wait a minute. Oh no, I have a meeting. Oh, I have to decide. Do I skip my meeting or do I see Tavares? I have to soul search on the way over. Okay, now, okay, so there's the outer. The outer integral just is that, x or y equals 0, y equals 8. The inner integral, x starts at radical third root of y. What does that look like? X equals the cube root of y? Well, that's the same as y equals x cubed. And that, I know what that looks like. That looks like this. So here's y equals x cubed. And so that's the same as that. And then where does it end? Ends at 2. Cube root of 2. I guess it ends right here. That's a weird region. So this is the region we're talking about. Okay, so now that we've got the region figured out, what we're going to do is we're going to replace the horizontal rectangle, because this dy on the outside means it's a horizontal rectangle, make it into a vertical rectangle. That's a delta x now. Let me just set this up for you. We won't do it fully, but once we have it set up, it's not difficult to do. I know it looks scary, but it's not difficult. So notice that the outer integral, x goes from 0 to 2. The inner integral, y goes from 0, that red line there, to whatever this line is, that's y equals x cubed. So this is very doable. In fact, I could do it in my head. It's going to be 1/4 e to the 16th minus 1. I think that's the answer. Don't quote me on it though, but like I said, this is, once you have it in a form like this, it's easy to do. Homework is just, there's like 4 problems. So sketch the regions though, please do sketch. I'm going to stop the recording if you want to come talk.